Hello everyone. I welcome you again to the next session of fluid mechanics and we are discussing fluid statics. In today's class we will discuss pressure. So these are the objectives of chapter 2. We have covered first four objectives till now, and as I told you, today we are going to derive an expression for force exerted by the fluid on submerged surfaces, wherein we will take into consideration the inclined surface as well as a curved submerged surface. So the first part is force acting on a submerged plane surface. So we have a surface over here which is inclined at an angle of theta. So this is basically your surface. This surface is inclined at an angle of theta and this is a liquid level or liquid surface. So this is your top view of that surface which is being shown over here, and we have designated this as an x-axis and this as the y-axis. So on this plane surface we have a system of parallel forces that basically acts when it is submerged. So first of all we will derive the magnitude of the total force which will be acting on this inclined plane surface. Secondly, we will try to derive the point or line of action of the force at which this force is acting. So we will try to identify first the magnitude of the force which is acting on this surface and the line of action of that particular surface. So as I told you, we have considered an inclined surface which is making an angle of theta with the horizontal. So in order to analyze this, we will take into consideration a area strip which is having a small area, that is dA, on the plane surface. So that surface area A will be over here, and in the top view if you can see that this will be the aerial strip which is at a distance of x from this axis, and certainly this area is over here, so it is at a height of, or it is at a depth of h from the liquid surface. So the force which will be acting on this surface which will be over here, which is being shown over here, this one. So the force acting on this strip is given by is small force, and it is given by dF, which is equals to P, which is the pressure which is acting on this area. So P can be written as rho GH, as you know, and dA is as it is, and H can further be converted into x sine theta, because if you take into consideration this triangle, you can find out, or you can write down h in terms of x sine theta. So this will be the force which will be acting on this small strip, that is dA. So in order to find out the total force which will be acting on this surface, or in the top view as I've shown you, this kind of surface, so the total force will be given by the integral of the force which is on the small area dA, and that is given by F, which is equals to integral of PdA, and we'll put these values over here and we'll get this type of expression, and it is simply rho g sine of theta integral of xdA. So xdA, we know that it is the first moment of area about the y-axis. So if we have this axis y, so it is your first moment of area about the y-axis, and it is also given by a into xc, where a is the area of this surface and xc is the distance of the y-axis to the centroid. We can write it as c as the centroid of the area, which is shown over here, and this is basically P, or center of pressure of this particular surface. So it can be given by a into xc. So we'll put this value over here and we'll get F is equals to rho g sine of theta into a into xc. Again we can convert it in terms of hc, and because we want to find out the force in terms of pressure, so xc sine of theta, this sine of theta plus this xc will be equals to hc if again we will take similar kind of a triangle over here, and f will be equals to rho g a into hc, and rho g hc will then be called as your pc, because rho g is your rho g into h is your pressure, so it is the pressure which is acting at the centroid, which is the pressure which is acting at the centroid. So the total force which is acting on the submerged surface is equal to the product of pressure acting at the centroid of the surface. The pressure which is acting at this point, simply we can say acting at this point into the area of the complete surface. So what we can say then, we can say that the pressure at the centroid, this is your centroid, is the average pressure acting on the surface. So if you want to find out what is the pressure which is acting on the surface, then you simply have to find out the pressure which is acting at the centroid of the surface. It will certainly give you the magnitude of the force which is acting on this complete surface, okay. Now, in that case, you are only taking the pressure which is due to the height of this liquid, which is creating some pressure on the surface. But as you all know that we have also some atmospheric pressure which is acting on the surface. Okay, so that if you want to consider that pressure also, we will simply add the atmospheric pressure term over here, and we will get this equation in the modified form, and certainly this is the force which is acting on this complete area, okay. But basically it is your magnitude, it is the magnitude of the force which is acting on this, okay, complete area. So secondly, we want to find out the line of action of the that particular force. Magnitude we have now calculated that it is after this derivation we have got this value that this will be your magnitude. But as far as your line of action of that force is there, that line of action of the force is certainly not at this point, it is certainly at some uh, length below this point, certainly the center of pressure, basically it lies along the line of action of the total resultant force, so it is certainly at some distance. So we want to find out the location of the line of action of that particular force. That's why we have shown the force over here, because magnitude we will find out by this method, but the line of action of the force will be it will be at the center of the pressure. So center of the pressure we will try to locate in the next slide. Okay, the point of application of the total force gives the center of pressure and can be determined as follows. So in order to find out, this center of pressure point P, we have assumed that it is somewhere down, somewhere at certain distance from this. So, but now we will try to find out this XP basically. We have assumed that it is at certain distance, that is xp, and certainly if you will take into consideration from the topmost level of the liquid, then it will be hp. So we will try to find out these hp and xp terms over here. So we will take the moment again, we will use the basic principle. We will take the moment of the pressure force df acting on the area. So we will take the moment of this force, okay, which is acting on this area. So m is equals to df into x, moment about y-axis we will take, and certainly df into x, and we will convert it into, df will be converted into your pressure into area, because it's a force is equals to pressure into area, and pressure is equals to p is equals to rho gh multiplied by area. So we have this term again. We can write h as x sine of theta, as we did in the previous case from you from this triangle. So we can then write it as rho g x square sine theta into dA. So since it is a moment of a very small area, so we have all the areas over here. Uh, so all the areas will be there because we have a number of strips which will be encompassed by this complete area. So moment of all those small areas will be given by the integral of this moment which we have obtained over here. So integral of all these moments will give you the moment of the complete surface or the total surface area about the y-axis. Okay, so we can write it as rho g sine of theta integral of x square into dA. Now this x square into dA, we know that it is your Iy, or it is the second moment of area or moment of inertia about the y-axis. So we can simply write it as Iy. Okay. So we have this equation. We will remember this equation. It is equation number 1, which is giving the moment of all the areas or moment of the complete surface about y-axis. Secondly, we also know that force is equals to rho g a into hc, which we derived in the previous case. So it is certainly the force which is acting on the complete area. So if we will take the moment of this force, and that moment of force along the y-axis we will take, we can write it as F into xp, because we are assuming that this force is acting at another point which is at P, and it has some distance xp from this axis y. So F into xp is equals, we can write this as this moment as, F into xp, and it will be equals to rho g a h c into xp, because we have used this force over here, and so it can be written likewise this. So it is also the second case is also the moment of the complete area, and first case is also the moment of the complete area. So we can equate these two equations. We can equate these two equations, this equation and this equation. So this equation is equals to this equation which we have obtained over here, and we calculated, and what we got is that Iy is equals to a into hc into xp divided by sine of theta. Now if IC is the moment of inertia of the surface about the axis passing through the centroid. So let us suppose again, as I told you, that this will be your centroid and this will be your center of pressure. So if IC is the moment of inertia of the surface about the axis passing through the center. So by using the parallel axis theorem, what we can do is we can find out Iy. So Iy is equals to Ic plus Axc square. This parallel axis theorem you have learned in your previous prerequisite, that is your engineering mechanics. So Iy is equals to Ic plus Ax square. So what we will do is we will again put this value in the previous equation, which we came to know about in this previous slide. So we will put these values, and this Iy is equals to Ic plus Ax square. So we'll put the values over here. This is the previous equation. So rho g sine of theta Ic plus Axc square is equals to rho g Ahc into xp. Okay, so this is the equation. So we will now try to simplify this equation, and xc over here is the term, hc over here is the term, this is xc, and this is hp, xp, sorry. So we will try to find out xp, and say this is your xc, and again this is your xc. So again, by using this triangle, we can find out xc, and we can find out, again using this triangle, we can find out xp. So this xc and xp is this. So we'll put xc and xp over here, and substituting these values in the above equation, and after simplifying, what we will get is that this hp is equals to Ic sine square theta by a into hc plus hc. So basically, what was our objective? We were supposed to find out this hp or this xp, because we want to find out the line of action of the force which is acting on that particular surface. So and this line of action of the force is certainly at certain some depth, that is your hp, and consequently we can convert it into xp. We can also convert it into that. So hp is basically hc plus some value, because hc is there, this is hc plus some value is there, some addition will be there. So that addition is basically ic sine square theta into divided by a divided by hc. So it certainly means that from this equation we can also say that the line, the point of action of the force will certainly be below the centroid, because this, if you take this into consideration, so hc is over here and hp is over here, so it certainly means that it is below the centroid by certain amount, and that amount is, that magnitude is your this one. Okay, so we have the special cases over here. Suppose this plane surface is an horizontal one, suppose this surface is likewise this. Okay, it's a special case, or it is a simple case. So in that case, what will be the case? This sine of theta will be this, your theta is equals to uh, 0, and certainly sine of theta will also be equals to 0, and if you will put the sine of theta equals to 0, then in that case hp will be equals to hc. So this is a case when we have a horizontal surface. In that case, force will remain same, it will not change, which we have derived in the previous slide, but your point of action, line of action over here will remain same in case of your horizontal surface. These, because hp, if it is a horizontal surface, suppose it is hp, similarly it is, there is some hc, so it will be having the same depth, same height. Okay, so it means that the centroid and the center of pressure are at the same level in case of your horizontal surface. On the other hand, if you're taking into consideration a vertical surface, where vertical surface means the surface is likewise this. Okay, so in that case, sine theta is equals to 1. We will put the value over here again, and this equation hp will now be ic by ahc plus hc, which certainly means that at some point we will have centroid, and below it we will have a center of pressure. Likewise, we have seen over here, below this will be center of pressure, and this difference is this difference. Okay, so for vertical case, we also know what will be the point of action of the force, or line of action of that particular force, and for horizontal we also know, and for inclined we also know the line of action of that particular force. But the fact of the matter is that your magnitude of the force will remain same, and it is certainly the pressure multiplied by it is certainly the pressure which is acting at the centroid multiplied by your distance of the center of distance of your centroid from this particular axis, that is your xc. In that case, it will remain same in each and every case. So the next part is the force which is acting on a submerged curved surface. It is also very important to understand what is the force which is acting on the curved surface. So in that case, the easiest way is to find out the parallel and the perpendicular components of the force, because since it is curved surface, so we can resolve the forces into x direction as well as in the y direction. So let us consider a curved surface. This is basically a curved surface, this one, 2 3, this is a curved surface. Okay, it can be it can be extended likewise this, it can be extended likewise this, or it can go towards that side, or it can go towards that side, but we are interested to find out the force which is acting on this curved surface. Okay, so we will assume that curved surface which is submerged in a liquid which is having some density rho. For the analysis of the forces acting on the curved surface, we will consider a block of liquid. So we will basically consider this block of liquid which is shown in orange color over here. We will consider this block of liquid which will encompass some liquid in that. So we will try to find out the force which is by means of which is acting on this liquid block. So in this case, what we'll do is the vertical surface 1 2, this vertical surface 1 2 is basically what it is, the projection of this curved surface on that area. So if you'll see the projection, if you'll see if you throw some light, the concept of projections, if you'll throw some light from here, and if you'll see the curved surface projection, you will find this kind of area. Okay, similarly, if you throw some light, project some light from this, you will see the projection in the horizontal surface, and it will be given by 1 3 surface, and the vertical projection will be given by 1 2 surface. So the force which is acting on the vertical projection will give you the horizontal component of the force, and the force which is acting on the horizontal projection will give you the vertical component of the force. So we have to find out these two vertical components, and the resultant of these two components, not vertical components, these two components, that is horizontal as well as the vertical component. So the resultant of these two components will give you the resultant force. So we have considered that particular area. Once again, let us consider a very small elemental area dA over here on the curved surface, which is inclined at some angle theta, angle phi. So the force which is acting on this small area, we have taken an elemental area of this curved surface. The force which is acting on this area in the horizontal direction will be given by dFH, and it is equals to dFr into sine of phi. Similarly for your vertical force, and we can write the total force which is acting as the integral of the force. And since the force is given by pressure into area, so it is written over here P into dA, and again we can convert P into dA in terms of P we can convert in terms of the height. We have assumed that this small area is at a height h from your top level. So we can write these equations for your horizontal surface and for the force which is acting on the vertical projection, or the vertical component of the force. Now the most important thing over here is horizontal force is okay, but in vertical force we have to take, if you want to take into consideration the total force which is acting on the vertical direction, we have to take into consideration the weight of the fluid, that that we have to take the body forces into consideration also. So body force will be due to the weight of the liquid which is encompassed in your liquid block. So if W is the weight of the liquid encompassed in the block, then the total force in the vertical direction is given by Fv plus the weight of your liquid. Okay, so weight can be given by your mg. Okay, so if the curved surface is above, there can be another case wherein the curved surface can be above the liquid block. This is the realistic example of that. Suppose we have this kind of a shape, and it is curved one over here, and this kind of a container. So here we can find out what will be the force which is acting. We are not interested in that. We are interested in finding out the force which is acting on this curved block. So in that case, again, we will analyze the system in a similar way, but the vertical force component will be given by the force will be acting on the surface will be in the upward direction. So the vertical force which will be acting on this surface will be given by Fv minus W, because weight will act in always in the downward direction. So the force in the second case will be Fv minus W when we are taking this curved surface into consideration. So in the nutshell, what we can say, the forces which are acting on the curved surface in the horizontal direction, it will remain same, it is the Fh, whereas in the vertical direction the force can be Fv plus minus W, depending upon what? Depending upon type of the curved surface you have, or depending upon the liquid, whether it is above the surface or whether it is below the surface. So we have to adjust accordingly to find out the vertical force. Okay, and horizontal force will remain same, and Fv and Fh we can find out by using these formulas. And certainly if you want to find out the resultant force which is acting on the curved surface, that will be given by this particular formula, which will give you the resultant force. So this was all about the forces which are acting on the curved submerged surfaces. So these were the books which were taken into consideration during the course of action. So in today's class, we discussed an important part, important aspect of your fluid statics, that is your pressure on the submerged surfaces, whether it is an inclined surface, it is your horizontal surface, it is your vertical surface, or it is your curved surface. So I thank you very much for watching this video. Thank you.